In this unit, we begin to actually think about chemical reactions in a different way than we've thought of them in the past. In the past, a chemical reaction has always been two or more elements or compounds that have reacted, they've combined, they've traded partners, they've done something to change what the actual compounds are that are involved, and the original compounds are no longer there. That's the key thing that's going to change right now. We still have elements and compounds reacting to form new ones, but now we need to change the idea of having no reactants left. The old way of thinking, we could have called chemical reactions one-way events. We begin with the reactants, we end with the products, and we are done. In previous science classes, this was a really good way of distinguishing a chemical change from a physical change. A physical change was something that could be undone. Melting ice, freezing ice. If we change the temperature, we can turn that ice back into water. We can turn the water into ice. A chemical change was something such as frying an egg. It could not be undone. Well, things change now. That's not always the case. It is actually possible to unfry an egg with the right amount of technology and the right amount of money. A lot of chemical reactions can be what's called reversed. They're reversible reactions. So we can take, let's say, salt, sodium chloride, as a solid. We can put it in some water, dissolve it, turn it into an aqueous solution dissolved in the water. But we can also go backwards and take that dissolved sodium chloride and turn it back into a solid. So the old idea of reactants being used up to form products and then they're gone doesn't actually apply anymore. To put that in perspective and see what that means, we'll take a look at nitrogen dioxide, NO2. NO2 is a reddish-brown gas. It's got a rust color. We can react it, we can change the pressure of the container that it's in, and we can form dinitrogen tetroxide. And the chemical equation for that is here. We can then change the conditions, and we can turn dinitrogen tetroxide back into nitrogen dioxide. We can actually go both ways. We can go forward, NO2 into N2O4, or we can go backwards, N2O4 into NO2. Now, we don't actually write both reactions separately, we actually combine them together now. The only thing that changes is the way we put the arrow in the chemical reaction. We don't put it as a one-way arrow anymore because we know we can actually proceed both ways. So we put it as a double-headed arrow, just as an indication that yes, this reaction can proceed both ways. It is reversible. It's not the products form completely out of the reactants. We have some reactants and some products at all times. We need to be able to talk about which direction we're talking about because the reaction can proceed both ways. We can talk about the forward reaction, which would be the chemical reaction the way that it's always been written. So just to step back, this would be considered the forward reaction because it matches the direction of the double-headed arrow. We can talk about the reverse reaction because it is actually going in reverse from the way that the reaction is written. So we will be talking about the forward reaction, left to right as usual. We'll also be talking about the reverse reaction, right to left. So as I've already mentioned, dissolving salt in water, the chemical reaction for that is NaCl solid reacts to form NaCl aqueous. Now what happens is we put the salt in the water, we stir it up, it dissolves. It goes from solid to aqueous. We keep doing that. Eventually we will get to a point where no more salt will dissolve. And we'll have a pile of salt sitting at the bottom of the beaker. That type of solution that we have is called saturated because no more salt will dissolve. Now to the naked eye, on a large scale, it looks like the reaction has completely stopped. We've got a pile of solid salt sitting at the bottom of the beaker, and the salt that's dissolved is staying dissolved. Well, on a microscopic level, what's actually happening is a continuation of this chemical reaction. We have little bits and pieces of salt that is actually precipitating out or becoming a solid, bonding onto the crystals that are sitting there, and little bits of the crystals that are dissolving back into solution. We can see that on a microscopic scale, but we can't see it on a macroscopic scale. That point where those reactions are happening at the same speed, where we can't see any changes, is called equilibrium. It is the point at which the rate of the forward reaction equals the rate of the reverse. It's the point at which the speed of the salt dissolving equals the speed of the salt solidifying. Like I said, we can't see any more changes on a large scale level, but on a small scale level, those reactions are still happening. And I've put this twice because it is incredibly important. The rates, the speeds of the reactions are going at the same speed. This does not always mean that we have equal amounts of reactants and products. Sometimes we have more reactants, solid salt. Sometimes we have more products, dissolved salt. And that depends on the types of compounds being involved in the chemical reaction, along with the different conditions that are involved. The temperature the reaction is happening at, the pressure, and other factors that we'll talk about later on. A different chemical reaction, we take some hydrogen gas and some iodine gas. Those will react in a closed container. They'll form hydrogen iodide. And measurements happened, and at equilibrium we found the concentrations of each of those. And concentration is something we talked about in Physical Science 20. The unit of capital M stands for molarity, meaning how many moles are dissolved in 1 liter of water. And looking at the values that we have, the reactants, H2 and I2, 0.022 molar, very small, and HI has a concentration of 0.156 molar. So we can see we actually have more products than we do reactants, but the speeds that the reactions are going on at has equaled out. We can talk about this in terms of favoring one side or the other, and since we have a higher concentration of products, we'd say the product side is favored. Other reactions, we'd have the reactant side as favored if the reactant concentration was higher than the product concentration. Something that might make this make a little more sense, think about an escalator, the down-going escalator. You start at the top, and when you're at the top, you can consider yourself completely reactants. At the bottom of the escalator, that's the end of it, you can consider yourself completely products. As the escalator goes down and you're standing on it, you turn from reactants into products. Now, let's say you get halfway down the escalator, and you start walking up at the exact same speed that the escalator is going down. That's an equilibrium system. Somebody standing off to the side would not see your legs moving, they would just see you standing still. Now, the escalator is doing some work moving, you are doing some work moving up. Those are the microscopic changes. On a macroscopic, large-scale level, somebody standing off to the side could not see your legs moving. If you decided to start walking closer to the top, you would be on the reactant side of the reaction. If you waited until you were almost at the bottom, you would be on the product side of the reaction. So this is a dynamic system, meaning changes happen. The reactions continue to go on, even though from the outside, from a large scale, things appear to have stopped. It doesn't matter for the escalator where you decide to start walking. As long as you start walking and you match the speed of the escalator, you match the speeds of the reaction, you have an equilibrium system. Keep in mind, though, that for equilibrium to happen, we must have a closed system. We can't add in additional reactants, we can't siphon off products. If we're talking about the escalator, we can't have somebody in the control room changing the speed. You are not able to change your walking speed. Everything happens as it is. In the chemical reaction, let's say we were able to siphon off the HI, the product. We couldn't get to an equilibrium because that system would keep trying to produce HI until it got to an equilibrium, and it would never be allowed to accumulate. Now, on a graph, what does that look like? Well, we have the rates of reaction. At the beginning of the reaction, the forward reaction proceeds very quickly because there's no products there to contribute to the reverse reaction, nothing to slow it down. And the reverse reaction starts off very slowly. But as time goes on and the reactants get used up and we have more products, now we have more products to react, so the reverse reaction speeds up. As we use up the reactants, the speed of the forward reaction slows down because we have fewer reactants to use up. Eventually we get to a point where those reaction speeds even out and match each other. And this here, when those speeds match each other, that is when we get to equilibrium.